Yeah, he asked if he wanted to bring a cowboy hat to school tomorrow. I was like, Sean, that's up to you, man.
Alex, remind us one thing we did in the lab.
What?
What's one of the things we did in the lab?
We heated up very sulfate.
Okay, good. Why, Blake?
To see the changes in it.
Like what change, Abby? Did it change color? What else did it change? Change mass. Why did it change mass? Because it was losing moisture. Okay, so so we heated copper sulfate. And there was water on the copper sulfate that we dried out. So we can write that like this, so it just has water in it. And we dried it out. Right? This compound together was blue, and then when we dried it out, it was copper sulfate. And the water, where's the water at?
In the air.
In the air, right? Right. So the water's in the air. The initial mass was this together, and pretty much the average mass that everybody started with was something like less than 4 grams, something like that. So we started out with some grams of copper sulfate in water. And then the mass decreased, and so we ended up with some grams of copper sulfate by itself. And the change in this, when the mass goes down, what does that decrease in mass tell us?
How much water is there?
How much water. So we also know how many grams of water. Okay. And so the purpose of the lab was to get an idea about how much water is there per copper sulfate. Okay? And so we can find a ratio between the copper sulfate and the water. How much water should there be?
None.
Well, do we know?
No.
Well, we're going to find out, but like, what I'm getting at is, what's the right answer? How much water should there be?
However much you measured out? Or
None.
as much as let off of the copper?
As much as let off, but do we know how much that's supposed to be? Like, what is it supposed to be?
It's not supposed to be.
It could be. Here's the point. So we did, between the 3 classes, we did all these tests. Okay? And if you want, actually bring your computer up and go to the data sheet on your lesson plan. And we're going to talk about some things, because we're going to bring up accuracy and precision. Because we want to get at this idea about what is it supposed to be? And how are we going to decide what it's supposed to be? And then what's that going to tell us? Okay? So, if you look through there, did we all start with the same mass of copper sulfate?
No.
No. Okay? And that's a good thing. Okay? But regardless how much we start with, should the ratio be the same?
Yes.
Should be, because we all took it out of the same container. Okay? So let's take a look. So we start with a variety of different masses. We dry it out. We find the mass of water. Okay? Should the mass of water be the same? No, right? Because the mass is going to depend on how much we start with. And since we started with different amounts, the water is going to be a different amount. So that's why we reduce it to a ratio. Right? So we divide it by the smallest one, and then that kind of puts it on a level playing field. So, if we divide it by the mass of water, notice then that the water is all one. Right, so if we compare it to water, water is all one. Okay? When we do that now, should the copper sulfate all be the same? Ideally, yes, it should all be the same.
In theory.
In theory, it should be the same. Is it the same?
Not typically. I mean, sometimes.
Sometimes it might be, right? Okay, so if you look through there, right, we've got a small range, right? Like, what's the smallest ratio of copper sulfate we have? If you look through the ratio of copper sulfate white, what's the smallest value in there?
0.09.
0.09? Where's that at?
At the second from the final mass, unless you're looking at initial mass.
No, I'm looking at this guy right over here. Ratio of copper sulfate.
Oh. Yeah.
0.13? Okay. And what's the largest ratio?
1.3.2.
Within column E. 1.87?
0.73.
1.87?
Oh, yeah, 1.87. Yeah.
I think 1.87.
Yeah.
Okay, so we have this range. 1.83. Okay. All right. So we have a range. So we're going to try to decide what the right answer should be. What are 3 statistics that we could do to kind of summarize? Because this is a range, right? How are we going to pick which one? What are 3 statistics we can do to kind of give us a picture of what the data looks like?
Median mode.
Okay. Yes.
Like the average.
Average. What would the average tell us?
Like in theory, that's what it's supposed to result. Sort of, kind of.
Sort of, kind of. Right. I mean, because by definition, the average is add them all up and divide by how many there are, right? So it just tells us the average. Have you ever thought about what the average really means?
The average means just that's the most frequent answer.
Oh, the most frequent.
Yeah, like the most common result.
That's something else. What were the other words you said?
Oh, median mode.
Median and mode. What's the mode is the most frequent.
Oh, so that might be the most common result.
So yeah, so the mode is the most common result. Okay.
The average might be like what it's around.
Okay, the average is like what it's around. Okay. Then the mode is the most common number. Okay. So if you get 1 like 5 times, that would be the mode. Okay. What about the median?
What's in the middle?
What's in the middle? So the median is here's our range, right? If we took all the numbers, all the results, and we ordered them from least to greatest, and there were 10 of them, if there were 11 of them, then like the 5th one would be like in the middle. Okay? What would that tell us?
That much is the most. That one's the in between the 2 biggest numbers.
I see that as like it can go either way. Yeah, it's a halfway point.
Yeah, there's this many results on this side of this number, and
Yeah.
there's this many results on this side of this number. They're the same number of results on both sides, and this is just the one in the middle. Okay. Yeah, so those statistics, and I bring that up because you're doing your STEM project, and so when you're talking about the average, because that's typically what you might do, right? If you're growing plants and the average height that the plants grow is 2 centimeters, what does that tell you?
The average is 2 centimeters.
Yeah, the average growth is 2 centimeters. What does that tell you?
That most of the plants are going to grow 2 centimeters.
And so if I take those seeds home and I plant them in my garden, I should expect
2 centimeters a day.
I should expect the average, right? I should expect that some of them are gonna be a little less, and some of them are gonna be a little more, but 2. Why don't, okay. For this data, that's what I did. The average, 1.42. Okay, that's the average. The median, 1.54. And the mode, 1.76. Okay. Think back to accuracy and precision. What did accuracy mean?
How close it was to the expected answer.
How close it was to the expected answer? Okay. And what was that? Accuracy or precision? Accuracy is close to the right answer. Precision is
Like,
Being cautious.
how consistent.
yeah.
Right. All right. Of these, which one would tell us consistency?
Precision.
Which number?
Oh,
Consistency would be average.
So consistency is how many times we're getting, how many times we're getting
it
the
would
right
be our
answer.
mode.
The mode. Right? So the mode's gonna tell us how many times, how many times we're getting to the right answer. We don't know what the right answer is. We're trying to decide what the right answer is.
There
Is the right answer 1.4, 1.5, or 1.7?
I don't think there is a right answer.
Oh, no, there is.
Oh.
Can you repeat the question?
Which number should we pick to be the right answer?
1.76,
Why?
because it's our most accurate, most consistent number on our model.
Because if we're doing that experiment and we get it twice, 3 times,
Yeah.
4 times,
Ah.
5, like if we get that number several times, like that's leaning us towards that's probably what it is, right? Okay, so that's good. If we pick the average, 1.42, why would we pick that? Or why would we not pick that? What are your thoughts?
Why would we not pick that?
Yeah, why would we not pick it?
Because it's too, like, as you said with the plant thing, like it could grow either above or below,
Okay,
so.
I'll give you a hint. Think about
You go.
the range. Why would we not pick the average?
I'll tell you later.
Okay. Why?
It's like, because it doesn't account for all the smaller numbers and the big numbers, it's just the difference.
Okay. If we look at this range, I mean, if we look at all those ratios, are we very consistent? No.
No.
Here's what we did. So the other classes, I had the other classes do this. They got to pick their own mass, and then I said, go pick another mass that's already been done and confirm that result. So, for example, I'll use Abby, sorry Abby, but Abby did this test here with 0.7 grams, and her ratio ended up being 0.13. I did the same one, pretty close to the same, 1.75, but what was my ratio? 1.68. So we have 2 tests that were pretty close to the same, but got very different results. What does that tell us?
Someone messed up.
Are we accurate? Are we precise? Okay. So either Abby's wrong or I'm wrong. Right? Or we're both wrong. Right, we're both right. Right. Similarly, here's one, Astrid and Raylan did this one, 1.41 and 1.41. What do you notice about that one?
That's the.
Reagan probably needs her computer up so that she can actually follow along.
That's the number.
Yeah, look at this blue one with Astrid and Raylan. They both tested 1.41 grams. What is the ratio?
The ratio. 1.76.
1.76. And it's the same.
Yeah, because they use the same numbers.
Where'd you get Raylan from?
Raylan's in another
Scroll
class.
down. Oh, I was
Oh,
like,
they're both in blue.
You
Okay.
said Ashton and Raylan.
Yeah, Astrid did this test.
Oh, I was so
1.4 grass.
confused.
Raylan
I
did
was
this test with 1.41.
I was like, that's Sherry. I was like, what?
Yeah, I was like, that's Ashton and Jerry.
You
But
really lost
okay.
me, but yeah, okay, thank you.
Oh, and what is 1.76?
The more.
One of our key statistics, right?
Yes.
Okay. What's another one we could look at? The green one. They both tested 1.89. Blake and I tested 1.89 as well. Blake got 1.49. I got 1.70.
It's because,
So those are a little closer together.
well, you guys got different masses for the final mass of the copper sulfate.
Yeah, we're 600ths off. But that's going to change our ratio. That's going to make our ratio. I mean, if we started like Astrid's and Raylan's, right? If they start with the same amount, we should expect to get the same result. So if we start with the same amount, we should get the same result, but we didn't. Okay. So are the tests super consistent? No.
Bless you.
So you guys think we should pick the mode as the right answer. Like that's what the answer is. What do you think?
I don't know, but I don't think that's right. I don't think it's the average median or the mode.
Okay, looking at that, what would you say? What would you pick?
I didn't pick any. I think there was no right answer.
You don't think
Because they're all different.
that's part of the point.
It's
I will say this, I would not pick the average because we have a very large range. I mean, this is a gigantic range,
Yes.
0.1 to 1.8.
Exactly. Because that's what you said with the plants. It could grow either above or below.
Yeah, there's way too much variability. So the average is not a good picture of what it should be because there's just too much variability. Okay? So that's why I would not pick the average. Okay? The mode's a good choice because if several people get the same answer, okay, then that's giving us confidence that that's probably what it is. But if you wanted to play it safe, you could pick the median, right? The median is like the average of the two, right? The median's the middle of the middle.
So it's even more specific, so that could be the right answer.
Could be, right? So I would pick the median in this case, and that would be my reasoning. The reason would be because it's between the average and the mode, and so it accounts that there is a little bit of variability.
Wouldn't it be better to tell the ratio if everyone started with the same?
Yeah, that would be a way to do it. But looking at the results, if we all started with the same mass, would we all get the same ratio?
Not the same, but pretty
No, not necessarily, right? Because in any experiment, there's going to be some variation.
We get closer.
You're going to get close, and we'd probably be, we'd have some more confidence. But here's the bigger picture. The point that I want to make is, should it matter how much we start with?
No.
No, it shouldn't matter how much we start with, right? And that's the bigger idea. When we're trying to understand what's happening, if we tested the same mass over and over and over again and get the same result, great, perfect. But that doesn't tell us, well, what happens if we have more or less? Are we going to get the same ratio? We should. So yeah, the bigger picture is it doesn't matter how much we start with, the ratio is the same. Okay? Mass. Okay, so here we go. which one are we gonna do the mode?
Yes.
Okay, so here's the answer. The answer is, for every 1.76 grams of copper sulfate, we have 1 gram of water. That's the answer.
Wow. So that means everyone has 1 gram of water?
Yeah, because we did the ratio, so everybody has 1 gram of water. We did it per, right? Copper sulfate per water.
Oh, yeah.
Okay? So for every 1.76 grams of copper sulfate, there's 1 gram of water. Why is that the wrong answer?
I don't feel like it's right.
Because
Look at it very
people-
carefully. Look at the formula, look at the masses. Why is that the wrong answer?
Because if people have a number less than that, they're still gonna have 1 gram of water. See, like,
So, well, we're right. I'm gonna do it per. So, do you see what we did here? If I'd had 1.76 grams of this, I had 1.09 grams of this, and I had 0.67 grams of this. Do you see that to do the ratio, I divided this by 0.67 and I divided this by 0.67, so it's all in terms of water? So this is always going to be 1 because I'll always divide it by the water, so this will always be 1, and this will be whatever it is. This happens to be 1.63. So that's how we got those numbers. So in that one, for every 1.63 grams of copper sulfate, I have 1 gram of water. For every 0.13 grams of copper sulfate, I have 1 gram of water. For every 1.49 grams of copper sulfate, I have 1 gram of water. Well, we don't want to do it all, we just want to have one answer. For every 1.76 grams, we have 1 gram of water. What do you notice? What's that?
we can't just have 1 answer.
Well, we could pick any answer, but the point is it's the wrong answer. It doesn't matter which one we pick. Why?
Is it all equals 1?
Look at this guy. What do you notice?
Copper, sulfur, oxygen,
What?
hydrogen, oxygen.
Oh, where is the rest of the sulfur?
Wait. Does this have to do with the subscripts?
Keep going.
Well, copper has a subscript of 1 and sulfur has a subscript of 1 as well. Oxygen has a subscript of 4, but and it's taking out 2 hydrogen and 1 oxygen. Is that right?
Keep thinking.
So, do you know the
So pretty much, they can't make hydrogen out of that.
Not that they're making hydrogen.
But it
Well,
can't be deleted.
they're taking out because there's two warm subscripts. They're taking out two elements. Maybe.
Let me back up just a step. Mass, right? We measured the mass, and we did all this stuff, and so this is a mass ratio. So for every 1.76 grams of this, we have 1 gram of this. Why can that not be right?
Because there's no hydrogen. But there's no hydrogen. So how can it take?
Well, but there's no copper.
There's no copper. But
Because
there's only one copper.
Because the copper staying as a solid is not being released as a gas.
Maybe.
Like the water is.
Okay, let me give you another hint.
Because there's too many oxygen in that one.
Yes! There's too many oxygen! I was getting there.
I knew you'd get there eventually.
I was like,
How can that not be right?
Because some of the
there's 4
oxygen,
oxygen and there's only 1 going out.
because if the oxygen didn't, if a little bit of the oxygen didn't stay back, it would like explode.
What do we know? Okay, let's think back to what we read about. We already know, like, historically, that some compounds can exist in different ratios. What did we call this idea from the reading? The law of conservation of mass?
Oh.
Conservation of mass tells us if we have 1 gram, then all this should add up to 1 gram. Right, that's conservation of mass. This told us something different. If the mass of this, okay. If the mass of this guy is 1, and the mass of this guy is 3, what do we know?
1 gram's going into it. Right. Because
You know the next one?
oh no, because sulfur has a subscript of 1, so they add together the subscripts.
Okay, so they're all 1.
Yeah.
But
Because
what changed between SO and SO2?
there's 2 oxygen.
So if the mass goes from 1 to 3, why did the mass go up?
Because
Addition,
sulfur is
oxygen.
1 and then oxygen is 2, so
Yeah.
it's
So they add together.
So what's SO3?
4.
5.
Why 5?
Oh,
This, what changed?
it added 1
It added 1 what?
oxygen.
What changed?
What up to?
Added 2. Oh, added 1 oxygen, but then the sulfur.
Well, this added 1 oxygen, and what happened to the mass?
It went up by 2.
Okay.
Oh, so it's
So what changes from SO2 to SO3?
2 grams.
Add 1 oxygen.
Add 1 oxygen. So what should the mass go up by?
2.
So it's
2.
5.
So it should be 5.
And then
So it should be 5.
the next one's 7.
Ah, okay. What do we call that? Law of multiple proportions. Yeah, I'm not have to worry about that. All right. So, right. So they were doing this, and they're like, so when they do this, now what do we know?
How much the oxygen weighs?
We know how much the oxygen weighs. Yeah.
2 what?
Okay. To what? Right. But we know the mass. How many do we got?
4.
How many do we got?
10.
Why is that not right?
Because if the oxygen,
Because
What should the ratio be by mass?
2. It should be 4.
5 more.
And
But
Yeah.
that's not how it works.
Why does that not?
because
It's
for
for
every
doesn't
1 gram
equal
of
one.
every 1 gram of copper sulfate, there's however much, whatever else. Like it's like, or there's 1 gram of water for an amount of copper sulfate.
True, but what I'm trying to show you is we have oxygen in both compounds. Oxygen's in both.
Oh, right, because it's in water too.
Oxygen is in both compounds. Oxygen is there. Oxygen is there. Okay. When we dry out the water leaves. The oxygen is still there. That's the point.
Yeah, it
Okay. It would do something, right? But it's still copper sulfate, and we saw that because when we added water back to it, it turned back to blue. Okay. So the water just dried out. So this oxygen left, but those oxygen stayed. So if we just look at it in terms of oxygen, what should the mass ratio be? Because there's 4 times as much oxygen as this.
So it should be 1.
So it should be 4 to 1 by mass. Because if the mass, let's just say the mass of oxygen is 2, then what is the mass of this? 2 times
2
4?
to 1.
Oh,
8. So let's say 8 grams. That's the mass. There's 1 oxygen here. What's that mass?
No, 1. Or, no.
2 times 1?
2.
2 grams. Okay. So just looking at the oxygens, our ratio should be 4 to 1.
That makes
Yeah,
sense.
but how does the sulfur come into
That's a good question. All right, so we got copper, but so I just wanted you to see it in terms of oxygen. But okay, let's throw in that and throw in hydrogen. I mean, should the mass still at least be something like 4 to 1?
Yeah.
I mean, this should be way, way, way heavier.
Yeah.
Way heavier.
Then yeah, that person's not right.
So this gets us to like the next thing. In this lab, we were just looking at it in terms of mass. Can mass really tell us exactly what's going on?
No.
Mass cannot tell us what's going on. Okay. You know, the other idea is, how much does oxygen really weigh? Does it weigh the same as sulfur? Does it weigh the same as copper?
No.
Does it weigh the same as hydrogen?
Could, I guess.
Isn't hydrogen lighter than oxygen is?
We know that now. But when if you were sitting with this stuff trying to figure it out,
Well, then you
like,
wouldn't
how do
know.
you figure it out? Okay.
Because it takes more hydrogen in a like in water, it takes more hydrogen than oxygen to make it.
Why?
Because
Oh, actually here. Okay, so 2 ideas. Number 1, do elements weigh the same?
No.
No. Okay, and we're gonna talk about why. Number 2, when we're looking at a compound, how much we need is different than how many we need. In water, how many hydrogens do we need?
2.
We need 2 hydrogens. How many oxygens do we need? Why did that? In copper sulfate, how many coppers do we need? How many sulfurs? How many oxygens? Okay. If we were to make this from scratch, how much copper would we have to start with? How much sulfur would we have to start with? Okay, so how many is different than how much? So let's look at this. In this copper sulfate with water, how much water is there?
1.76 grams.
How many water are there?
Or 2 hydrogen.
All right, do you see? I mean, that's the question. Like, we don't know. I mean, we're gonna talk about how we figure it out, but we don't know how many water. We know how much water there is, but how many? Is there just 1? Is there 2?
1?
Is there 3 of them? Is there
3
4 of
maybe?
them?
Like how many compounds?
See the real one.
This is what we're gonna think about, because this then will lead to other things that we're gonna do. Like, okay, if we're gonna make copper sulfate from scratch, how much copper? You know that orange copper metal stuff? Like, how much of that are we gonna have to start with to make copper sulfate? We know that when we look at copper sulfate, there's 1 and 1 and 4, but like how much? Can I just pull an atom out of the container and stick it together? No, right? I'm measuring the mass. So the idea here is how much versus how many, and how do we determine that? Okay. Good. Are you thoroughly confused?
Yeah.
Good. Take out your book. Grab a book.
Do I still have this?
I don't need level.
Can I go to the bathroom?
Yeah.
Okay. Thank you.
Of course.
Alright. So we're gonna be back to let's jump to like 70. We'll do no, actually let's go to 66. We'll review a couple things and then we'll jump into the new stuff.
Today a normal schedule. No, there's some assembly.
What's that?
Yes.
Okay. Thinking about Dalton's theory, Dalton used like 3 ideas: law of conservation of mass. So our starting mass and our ending mass should be the same, right? It just doesn't disappear. Okay. Definite proportions. This gets to, hey Sherry, this gets to, does it matter how much copper sulfate we start with?
No.
No,
I have to.
right? So that's definite proportions. Doesn't matter how much we start with, the ratio is always the same. Okay? And then multiple proportions, we have 2 or more different compounds, same 2 elements. The ratio is all going to be whole numbers, right? We can't have a half of an atom. That's an important idea. Okay. Then we did some experiments to discover the electrons. So we jump over to page 70. Did we read about the cathode ray tube? Just to make sure. And did we read about the cathode ray tube? I think we did. It was in the video, yeah.
It is really cool, that's right.
Okay. And then so when I think about the atom, we have the electron. The electron was the first thing discovered. Okay. And then we have to have a nucleus that's positive. The electrons are negative. Where are things located? So Rutherford kind of started to do this refine the structure, like what the structure looks like. Where is the positive charge? What part of the atom?
The center.
The center. Okay. So Rutherford described the nucleus with a positive charge, and then the electrons were not in the nucleus. Okay. What else was significant about the nucleus?
Isn't it called the powerhouse?
It's not neutrons.
Wrong class.
Also have neutrons.
Well, it does have neutrons. It does have neutrons.
That's looking funny.
Yeah, there is, and we'll get that today. But Rutherford didn't discover the neutron. Rutherford only discovered the proton. And we should say that proton. Later, we will find that there is a neutron. But what is significant about the nucleus?
Surrounded by rings.
Is surrounded by rings with the electrons. Yep. What else?
Is this about the divisible and indivisible?
Not yet. What else is significant about the nucleus?
Don't you need less of the nucleus and more of the electrons?
For
It to not be, I don't know.
if we make an ion, yep,
Does it have to,
Yeah.
do
I
the
was
per
not
definition
very
have to be
sure.
balanced?
they don't have to be. But the nucleus does need a certain number of neutrons to be stable and not to be radioactive. Okay, what else about the nucleus? Maybe nucleus or maybe protons versus electron. Compare and contrast the proton versus the electron.
Proton repulsion and neutron.
Oh, let's say protons and electrons. Protons and electrons. Protons are positive,
Has pores.
electrons are
Negative.
negative, protons are,
Positive.
electrons are,
Electrons are negative, and the neutrons are neutral.
and neutrons are neutral. Protons are,
Positive.
we already established that.
Okay.
Protons, something different. Protons are,
Not
elec-
neutral.
are, electrons are,
Aren't they the same? Aren't they equal?
look at the table on page 74.
I know it's
I was gonna say,
What else does that tell you?
that's hard.
they're heavier.
Thank you. Protons are heavy. Electrons are light. Okay. Because we're trying to like bring in the lab, right? So, atoms have mass.
In fact,
Where does the mass come from?
the
The protons.
neutrons.
Protons. Later, we'll find out that the neutrons are also there. So, where does the mass come from?
The protons and the neutrons.
Protons and the neutrons.
So the nucleus.
Okay, so the nucleus, right? So mass comes from nucleus.
I'm so disappointed.
Okay?
So fun.
This is an important idea. How many protons does hydrogen have?
How many
One.
protons does hydrogen have?
Oh, right.
How many protons does helium have?
Dose.
Oh, yeah.
So how heavy should helium be compared to hydrogen?
Heavier.
Heavier.
Double.
Double. Heavier. Should be heavier. Oh, okay, all right. So should oxygen and sulfur be the same mass?
No,
No, they are not the same mass.
because they have different.
But should oxygen's mass be the same as oxygen's mass?
Yes.
Yeah.
Yes. Okay. So this is where we can come up with the 4-to-1 thing, right? If I have 4 oxygens, that should be 4 times as heavy as 1 oxygen.
So is that how you determine how many waters are in water?
Then if I have a molecule like hydrogen, like 2 hydrogens and 1 oxygen, how heavy is that? Just add them all up.
4.
I have 3 pieces of stuff, I just add them all up.
4.
If they all weigh the same. But does oxygen weigh the same as hydrogen?
No.
No, okay. But where does their mass come from?
Oxygen is. So oxygen is a hydrogen. It's just hydrogen.
Okay, so we're gonna okay.
9.
We're gonna start here on page 75 with atomic number. What's that?
So water is 10. Whatever. Because oxygen is 8 and hydrogen is 2. Hydrogen is 2.
Where'd you get 8? Oh, from the number? That's the number. The number tells us the number. We're actually gonna find out. Okay, so Reagan, you wanna start off on page 75, atomic number.
All atoms are composed of the same basic particles, yet all atoms are not the same. Atoms are different elements have different numbers of protons. Atoms of the same element all have the same number of protons. The atomic number, Z, of an element is the number of protons in the nucleus of each atom of that element.
Okay, do you get your periodic table? Take your periodic table.
In fact,
Sean's guide to.
It may not exist. We can find out together.
three tables.
Okay, on your periodic table, look at the key. What is the atomic number of hydrogen?
1,
1. What's the atomic number of helium?
What?
Helium.
2,
Lithium.
3,
Beryllium.
4.
Beryllium. Boron. Okay, so how many protons does hydrogen have?
Wait, hydrogen? 1,
I should be just.
Helium.
Questions?
Lithium.
3,
Beryllium.
4,
Boron.
5.
Oh, so the atomic number, which is the number in the box, the number of the box, tells you the number of protons. Okay. So, what does the proton do for the element?
Gives it weight.
It does give it weight.
Positive
protons are
charges
heavy.
it. Gives it positive charge.
Gives it positive charge, yeah. But it also gives it the identity. Like, hydrogen is hydrogen because it has one proton. And so if I had a single proton floating around and I stuck another proton on it, it would no longer be hydrogen anymore, and it would be helium.
In fact,
And it would do all the things that helium does. Like, what do we know helium does?
It makes your voice go.
It's light,
Makes your voice go like
makes your voice go funky monkey, right?
We put it in balloons.
Huh?
We put it in balloons.
Yeah. So, so you have hydrogen as a proton. If I stick another a proton on it, it becomes helium and takes on all those properties. If I stick one more proton on it, what does it become?
Lithium.
Lithium, which is a metal. So it goes from being a gas to being a solid metal.
Crap.
But if oxygen's a gas, how is lithium lighter than oxygen?
Yeah, that's a good question. Like, then why do we have some gases and some metals, and like, why is mercury a liquid? Like, how does it, like?
Because of those properties that they have.
Yeah, because that's the very simple answer, is that's the properties that they have. And so having that many protons and that many electrons, that is just the properties that you have, okay? So that when you get together with everybody like you, you just take on that characteristic of being a solid, liquid, or gas, okay? Or being a crystal, or being a metal or a non-metal, or a noble gas, or an alkaline earth metal, or whatever. Okay. All right. Let's jump to mass number now. So go to page 76. Okay, on page 76. Josie, read mass number.
Identifying an isotope requires knowing both the name or atomic number of the element and the mass of the isotope. The mass number is the total number of protons and neutrons in the nucleus of an isotope. The three isotopes of hydrogen described earlier have mass numbers 1, 2, and 3 as shown in table 3.2.
Boom. Mass number is protons plus neutrons. This is what I want you to think about. Mass. Okay. So, if hydrogen has one proton and one neutron, what's its mass number?
1. 2.
2.
Simple math.
Simple math. If helium has 2 protons and 2 neutrons,
4.
4. If uranium has 92 protons and 92 neutrons, what's its mass number? 184. Okay. Easy peasy? Okay.
wait, hold on. How do you find the neutrons? Is that?
That's a little bit harder. I'm just giving you some examples. Like if, and if, then this. Okay. The problem is, this is the problem.
But there's neutrons don't have a charge.
Sage, go to page 78.
Yeah, stop it.
Actually, go to page 79. On page 79, read average atomic mass.
Most elements occur naturally as mixtures of isotopes as indicated in table 154. The percentage of each isotope is in the naturally occurring element runoff is nearly always the same, no matter where the element is found. The percentage at which each of the elements isotopes occur is natural is taken into account when calculating the element's average atomic mass. Average atomic mass is the weighted average of the atomic masses of the naturally occurring isotopes of an element.
Okay. So we have a mass number, but then we have a mass average. Okay, so both of them are masses, but they're going to tell us something different. Okay, and the mass average is going to be the average with all the isotopes. So, what's an isotope? Do you remember back what isotopes were? Okay. Jump back to 77 and we'll read what I said. So, Blake, you want to read designating isotopes?
The isotope of hydrogen are usual in that they have distinct names. Isotopes are usually identified by specifying the mass number. There are two methods for specifying isotopes. In the first method, the mass number is written with a hyphen after the name of the element.
Tritium.
Tritium, for example, is written as hydrogen 3. We will refer to this method as hydrogen notation. The uranium isotope.
Did he cut his hair?
What?
No, he has a bun. He has a bun in. Most luscious bun you've ever seen.
Keep going.
Use isotopes for nuclear power. Oh wait, I haven't even had.
Hey, Sean.
Our partners.
Sean.
Yeah.
Lance has a mass number of 235 and is therefore known as uranium-235. The second method shows the composition of a nucleus as the isotope's nuclear symbol. For example, uranium-235 is written as 235-92U. The subscription indicates the mass numbers and the subscript indicates the atomic number. The number of neutrons is found by subtracting the atomic number from the mass number.
Okay. Alex, read there that next paragraph, table 3.3.
Where?
Right there in the middle of the page, table 3.3. Oh, thus. Oh no, table 3.3.
Table 3.3 gives the names and symbols and compositions of the isotopes of hydrogen and helium. Nuclide is a general term of any isotope or any element. We could say that table 3.3 lists the compositions of 5 different nuclides.
Okay, so we got an isotope. Okay, and the question was, how do we find the number of neutrons? Well, looking in there, how do we find the number of neutrons? Mass number minus atomic number equals number of neutrons. Okay, and the idea is, does hydrogen only exist as in one form? One proton, one neutron? Nope. Okay. If you look at that table, hydrogen can be one proton and no neutrons. So hydrogen can be 1 and 0, it can be 1 and 1, or it can be 1 and 2. Okay? In this case it would be 3 and 1, in this case it would be 2, in this case it would be 3. Okay? Are they all hydrogen? Because they all have one proton, and the proton defines who it is. So they're all hydrogen, but they don't all have the same number of neutrons. Because they have different isotopes. So isotopes then are forms of an element with different neutrons. And forms of an element with different numbers of neutrons. What does that mean? Go to on your periodic table, look at the mass of hydrogen. What does it tell you the mass of hydrogen is? 1.00794. What were these masses? Hey, Gabe. What were these masses?
2, 4, 9,
These masses.
1, 2, 3.
Why do we have all these decimals? What's the atomic mass?
It's an atom.
Average. Average of what? All the isotopes. Okay. So if we take, and it was a weighted average. Okay. So some of hydrogen is 1, some of it is 2, and some of it is 3. And by the time we weight that and come up with, we add them all up and divide them by 3. And what do we come up with?
1.00794.
Okay. What's the mass of helium?
4.002602.
Okay, well, helium should be, and actually it tells us there, helium, in the isotopes of hydrogen and helium, we have helium-3, it has 2 protons, 1 neutron. Helium-4 has 2 protons, 2 neutrons. If we take the amount of helium-3 and add it with the amount of helium-4 and divide it by 2, what do we get?
4.00264.
Okay. Relatively, how much of helium is helium-4?
Most of them.
Most of it, right? And then helium-3 makes it an average, okay? How much of hydrogen is hydrogen-1? Most of it. Okay. And then the other 2 make the average go up just a smidge. Okay. So, when they're developing the periodic table and they're trying to decide, well, what mass are we going to use? They have to consider that when you, a good one would be, what will we use? Oh, copper will be a good one because we'll use copper. What's the mass of copper? 63546?
Yeah.
That was a lucky guess. Okay, well, why 546? Because
There's a multiple.
there's isotopes. Okay, so if you have a container of copper and you scoop out some copper into your crucible, some of that copper is going to be regular copper and it's going to have this mass, right? And some of it's going to be copper with this mass, and some of it's going to be copper with this mass. And so the average mass of the copper in your little crucible that you're going to heat up is
63.5.
review question. Why is copper heavier than helium?
Because helium's a gas.
Yeah, why would copper be heavier than lithium? What's the mass of lithium?
The protons.
6.941.
Why is copper, which is a metal, heavier than lithium that's a metal?
Because the protons are different.
Because the protons are different. How many protons does copper have?
29.
29? 29 protons?
Yeah.
And lithium has 3 protons. Oh, so copper should be significantly heavier than lithium. How many protons does uranium have?
92. Oh yeah, 92.
92. What's uranium's mass? Look at number 92.
238.0289.
And it has 92 protons. So, I mean, uranium is significantly heavier than copper because it has
That number of protons.
plus neutrons, right? So 92, the difference between 92 and 238 is how many neutrons it has, relatively. Okay, so things have mass. Average atomic mass, molar mass, the mole. Okay, turn to page 80. That's the word next. Page 80, Sherry, read that paragraph on relating mass to numbers of atoms.
The relative atomic mass scale makes it possible to know how many atoms of an element are present in a sample of the element with a measurable mass. 3 very important concepts: the mole, something number, and molar mass. Provide the basics for relating masses in grams to number of atoms.
Okay, so 3 very important concepts. The mole, Avogadro's number, and molar mass provide the basis for relating mass in grams to numbers of atoms.
We talked about this before.
How many bricks do I need to make a ton? Give me a number.
57.
40, 57, whatever. Okay. How many feathers to make a ton?
2,000.
A billion?
He's gonna write it out. What a trooper.
Okay, boom, done. They both weigh the same. How come I need more? On your periodic table, give me somebody who's light.
Hydrogen.
That's like 3 too many.
Did I do too many?
Yeah.
100,000 million billion.
Because that's a trillion.
What's a trillion?
Same thing.
A billion?
9 zeros.
Hydrogen. Okay, hydrogen. Oh, I was writing. Give me something that's heavy.
Uranium.
Okay. How much uranium? Let's see. Let's say I have 1 gram of uranium and 1 gram of hydrogen. How many uranium do I need? 30? How many hydrogen do I need?
100.
67?
I was like, well, I don't know what it is.
Why do I need less uranium?
Uranium is heavy.
Why is uranium heavy?
Because it has more protons.
Oh.
Ooh.
Why do I need more hydrogen?
Because it has
Less protons.
So it's
Lighter.
lighter.
Like crap.
Okay, good. So this should kind of give us now a basis to think about this. I have 1.76 grams, and I have 1 gram. How many do I have? The question should be, I have no idea.
I don't know.
But
More so you should have more eyes.
because this, right, I'm just giving this to you, right, but this is the idea, right? We recognize that uranium is heavy, because it has more protons, so I don't need a lot of it to be heavy. I don't need it. Right? And hydrogen is light, and so I need more.
You should have more copper sulfate than
Okay.
Because copper has more pros.
Well, okay, so we can use the periodic table to kind of give us an idea, but, right? How many pieces really are there? Like in 1 gram of uranium, how many atoms are there? Like a bajillion. Is there any way to really know?
No.
You can probably figure it out.
Yeah, we're gonna figure it out. We're just gonna it's right there. Right. But same thing with hydrogen. Like how many atoms, really? Right? Is it really 1 billion feathers? And it seems reasonable because it's a ton.
Is that what moles are? Is how many is in the...
So the mole is this idea that gives us a way to think about how many atoms it takes to make a particular mass.
Oh my. A lot of atoms.
Josie's gonna give us the number.
It's in scientific notation.
It's in scientific, that's right, because it's big.
2.53 times 10 to the 21st.
A bajillion, right?
A bajillion.
Why so many?
It's crazy amount.
Because atoms are small. They are heavy, relatively, right? I mean, when you think about protons and neutrons, they're relatively heavy, but they're really, really small, and so it takes a lot of them to add up to make some mass. Think about, when I showed you the block of aluminum, like how many atoms have to come together before we can actually see it? A whole lot. Okay. Why is this idea important? Okay.
Because you can see the how many buffalo.
Well, it's the how many, right? This is why this idea is important. If we want to make water, how many hydrogens do we need?
1, 2.
We need 2.
Oh,
And how many oxygens do we need? 1, right? So that's how many pieces we need. We need 3 pieces. 2 pieces of hydrogen, 1 piece of oxygen, and we can make water.
But how much of that?
Okay? But do we work with things 1 piece at a time?
No.
No, because it's way too small for us to work with them 1 piece at a time. How do we work with them?
In large amounts.
In large amounts, like what I can put on the balance and mass it out. Okay, right? I can tons is too much, right? Brent, we work with it at grams at a time.
Kg.
Okay. What's that?
I said kg.
Yeah, kilograms. So, but to help us understand how atoms work and to better understand the structure, right? Because we recognize that protons and neutrons are in the nucleus, great, and electrons are not in the nucleus, great. But how do the electrons work? Are the electrons going to work a mass at a time or a piece at a time? A piece. When we think about making water, the electrons are going to work a piece at a time.
Yeah.
Okay. Alright. So, that's what we're going to jump into next time. We'll watch a couple videos next time. But we'll talk about these 3 things: mole, Avogadro's number of molar mass, and how we use those to
subscribe, and vote yes.
So you're